What is thermodynamics? What is time? And how does it tie into the second law of thermodynamics and how it relates to energy conservation and time invariance on a microscopic level?
Oh boy, you have a basket loaded with jargon. I'll try to answer in that sequence. First of all, thermodynamics, as the name proclaims, is the science of power, power from fire. So therme means heat in the Greek, and dynamis means force or power in ancient Greek. And um, and the pioneer who later became Lord Kelvin picked this name for the fusion or the merger of caloric theory with mechanics, which is
Hmm.
necessary because the steam was exhibiting uh, those two behaviors at the same time. You could heat it and then get the heat back through cooling. That's caloric theory, the steam. But the steam was also pushing things, would expand like a spring, and that was a mechanical behavior. Okay, and so is the science of power and how power comes, and it comes only if an input of heating, in this case the fire, uh, was available, meaning heating was consumed, and between the heat source and the power output, um, uh, for there must be a flow architecture that moves in order to convert the heating into mechanical power. And
Hmm.
of course, the story is slightly more complicated. Thanks to Sadiq Carnot, a portion of the heating has to be rejected to the cold ambient. So you need two temperatures in order to stick the engine between the two in order to get power. It's just like, by the way, this is what inspired Sadiq Carnot. His father, Lazare Carnot, was the guy with the ideas first, but they were all about mechanical systems. The heat engine runs like a water wheel, one that is turned by a stream of water that's high, and then it fills some buckets, and it rotates the wheel, and then the same water flows into the stream at lower altitude.
Hmm.
That's the design of any hydroelectric power plant, okay? So, okay, by analogy, the son, Sadiq Arnoux, another mechanical engineer, um, military, thought of heat the same way, that it comes from high, in this case hot. It turns a wheel, which obviously it does. That's called the cycle executed by the water inside the architecture. And then at the end of the cycle, it rejects a portion of that heat into the cold ambient. But the rejection of heat is smaller than the intake of heat, so the difference is the power that's produced to delivered to the shaft,
Hmm.
and that's the only difference. So I don't know how I got into this. So that's the answer to what is thermodynamics. Is the science. If you possess and of course it has two laws worth talking about: the first law and the second law. Um, and if you have this in your head, then you understand not only what moves and why it moves, but yes, if you make changes in the flow architecture, that's the design of the better locomotive, if you want, then you get uh, you get more power uh, per unit of heat input, more power, and therefore you reject less heat to the ambient. That's the other way to say that you create an engine that's more efficient. Um, and this is the history of not just thermodynamics, the discipline, but the history of engineering, the history of physics too, because physics is all of science is useful. You name the domain of activity, and you'll see that um, uh, you sooner or later you'll see that everything that's useful uh, is uh, is of the same nature as the power that comes from the shaft of that engine because it facilitates your movement. Your movement. Uh, I need to add, this is now from the Constructal law, that the power produced by all the engines envisioned by makers of engines and teachers of thermodynamics, that power is destroyed instantly uh, for the purpose of moving something and pushing a vehicle or turning the spindle of a lathe or something to manufacture something. All of that is the dissipation of the power. So, and that dissipation transforms into heat the power that you try to extract from the engine as something different than heat rejection.
Hmm.
Meaning that if you put together the engine with the user of the power, you end up with let's call it cohabitating couple that dumps to the ambient the same rate of heating that the couple, meaning the engine, received from the fire.
Okay.
So that is energy conservation, okay? That heating from the fire uh, driving the engine, then the engine drives the movement. All of that eventually is the dumping of the heating from the fire into the ambient. But in this case, because there was an engine, um, you changed the landscape, you changed the surface of the earth. Movement has happened because of human ingenuity,
Right.
which is the engine. So that's a huge difference. Um, so, and that ingenuity, okay, we call it science or whatever. The One of the big, actually, is the biggest thing that led to current lifestyle and prosperity and safety and um, um, all these things we take for granted come from the fact that uh, power, electric these days, power is very cheap.
Yes.
It's so cheap nobody asks. In fact, a lot of it you are not asked to pay. In the airport, you stick your thing into the plug in the wall and to charge. You get this is so. I'm ashamed when I accept the freebies. But it is the you say to the credit of those who improved and improved and improved, and then and they found and they still keep finding sources of what to burn, okay, what to burn,
Hmm.
meaning fossil fuels, but also these renewables. They have to be imagined like wind power. Then you have to develop a brand new technology of how to capture that power more and more efficiently. Is the same with there are many brands of this so-called renewable energy, um, which okay, they require ingenuity and um, but along the way, every watt of power produced becomes cheaper and cheaper.